In this video we're going to talk about all the gas laws, but first we need to define pressure. So all gases exert pressure on their surroundings. So this is basically just the gas always pushing on the container it's in. So two instruments that we use to measure pressure include the barometer and the manometer. So the barometer, it can measure the atmospheric pressure. So you can see the red thing is a bunch of liquid mercury, and then so the air outside pushes in on the mercury here, and then it pushes up this mercury column through this tube. And if you measure the height of this column in the tube that the air is able to push down, then that's the pressure of the atmosphere. And a manometer measures the pressure difference between a gas here and the atmosphere. So you can see we have the column of mercury again, and on this side the atmosphere is pushing down, while on this side the gas is pushing down. So here the atmospheric pressure is greater than the pressure of this gas because it's pushing it down further up this way. So both of these instruments involve measuring a column of liquid mercury. So that's why one of the units of pressure is millimeters of mercury. And this is the same thing as torr. Now we also have the standard atmosphere, which is just the atmospheric pressure. And pressure is officially defined as a force over an area. And so the SI unit for pressure is the Pascal. And since the pressure is force over area, the units of a Pascal are newtons over meter squared. So to convert between all of these units, 1 atm is equal to 760 millimeters of mercury or torr, and equal to 101,325 pascals. So the one we use most is probably going to be atm. So now we have all of these different laws. So Boyle's law says that if we multiply the pressure of a gas by its volume, then it will always equal the same thing. Or in other words, pressure and volume are inversely related. So if we increase the volume, then the pressure will go down. And if we decrease the volume, then the pressure will go up. So if we have 4 liters of O2 gas at 1.2 atm, and we increase the volume to 7 liters, then we can use this to find the new pressure. So anytime we multiply the pressure and the volume, it'll equal a constant. So that means the initial pressure times volume will equal the same thing as the new pressure times volume. So we can just use 1.2 the pressure times 4 the initial volume, and set that equal to the new pressure and 7 the new volume. So we can find that the new pressure will be 0.69 atm. So the pressure decreased when we increased the volume, which is what we'd expect. So Charles' law says that the volume of the gas is directly proportional to its temperature in Kelvin. So as temperature increases, volume also increases, because as the gas is moving around faster at a higher temperature, then it will expand. And this is at a constant pressure. All of these laws at a constant something. So here only the volume and the temperature are changing. So if we have a gas at 15 degrees Celsius that occupies 2.58 liters, and we increase the temperature to 38 degrees, we can find the new volume because V divided by T is always a constant. So we can just plug the initial volume and temperature in and set that equal to the final volume over the final temperature. And make sure with these gas laws that you convert your temperatures to Kelvin. So the final volume will be 2.79. So the volume increases as well when we increase the temperature. Now, sometimes you also have to know Gay-Lussac's law, which is that the pressure is directly proportional to the temperature at a constant volume. So if we increase the temperature, the gas particles are bouncing around the container faster, and so they hit the container more often and with greater force, which increases the pressure. Now, the last one is Avogadro's law, which says that the volume of a gas is directly proportional to the number of moles if the temperature and pressure are constant. So, if you have more stuff, then it takes up more space. So, now we can just, if we solve for V in all of these laws, and we find that the volume of a gas is directly proportional to the temperature, the moles, and 1 over P, the pressure. So if we combine all of these laws into one big law, we get that the volume is proportional to the temperature and the moles over the pressure. And instead of writing K as the proportionality constant, we can write this big which is called the universal gas constant. And the value you use most with the gas problems is going to be 0.0821 liter ATM over Kelvin mole. And you can find the units for this constant because this side, the volume has to be in liters. So we need a liters here on the top. And then we need to cancel out the pressure on the bottom, which is an ATM. So we need an ATM on the top to cancel out the pressure. And then on the bottom, we need to cancel out the temperature and moles. So we have Kelvin and moles on the bottom. And so if we rearrange this, we get the familiar ideal gas law. PV equals nRT. So if we have a 0.35 mole sample of argon gas at 13 degrees Celsius and 568 torr, and we heat it to 56 degrees Celsius and 897 torr, then what is the change in volume? So the first thing you want to do is convert everything to the right units. Remember, for the ideal gas law, if we want to use that value of then we need the volume needs to be in liters, the pressure needs to be in ATM, the temperature needs to be in Kelvin, and moles are just moles. So we convert the temperatures to Kelvin and the pressures to ATM first, before you do anything. And then we can solve for the initial and final volumes. So the volume will just be nRT over P. And so we get the initial volume is 11 liters and the final is 8 liters. And so the change in volume is the final minus initial, or negative 3 liters. Now, oftentimes when dealing with gases, we are at 0 degrees Celsius and 1 ATM. So these conditions are called standard temperature and pressure, or STP. And at STP, any 1 mole of any gas has a volume of, we can solve it for in the ideal gas law. So 1 mole of any gas will have 22.42 liters at STP. So you'll often use this number when doing stoichiometry with ideal gases. And we can also find a relationship that includes density and molar mass in the ideal gas law. So we can write the moles of a substance as the mass divided by the molar mass, or little m over big M, where where big M means molar mass. And the density of a gas is the mass over the volume, or the volume equals the mass over the density. So if we take the ideal gas law and plug these expressions in for V and N, we get this, and then the little m, the mass, will cancel out. So we can get the molar mass of an ideal gas is equal to the density times and the temperature divided by the pressure.